Hi, I'm Zor. Welcome to Unizor Education. After we spent some time introducing the concept of a vector, well, let's try to analyze what exactly we can do with this, what its characteristics, etc. So, today's lecture will be about one of two main characteristics of the vector. The main characteristics are magnitude and the direction. So today we will talk about magnitude, and considering that the vectors represent certain physical or geometrical quality of some object, we can talk about the lengths of the vector, basically. So the magnitude as a philosophical concept is represented in the lengths of the vector. Now, if vector is represented graphically, like this particular arrow-headed segment, the lengths must be measured in certain units. So, for instance, this particular vector represents a speed. Well, speed can be measured in meters per second, or miles per hour, or whatever else. So, somewhere we should have a unit of length which is equal to, let's say, 1 meter per second. And then, depending on the lengths in these units, this geometric representation of the vector has certain lengths, like 5.7, for instance. It means the speed is 5.7 meters per second. That's what exactly this represents. Now, this is kind of trivial and easy. Now let's talk about the analytical representation of the vectors as tuples, as ordered set of numbers which are related to coordinate system Let's say we are talking about two-dimensional vectors. So this vector has certain coordinates, a, b, and the tuple a comma b represents the vector because it represents the end point of a segment which is originated at point 0, 0, obviously, and so this particular segment represents both the magnitude, which is represented in its lengths, and direction, which is represented basically by the direction from the point 0 to point a comma b on the coordinate plane. Now, considering we know only a, b about this particular vector, we don't have it visually, geometrically, we don't have anything, we still have to determine its lengths. Well, but let's think about what is a coordinate system. Coordinate system is something which also has certain units of measurement on each axis, right? So the unit of measurement is given because the coordinate system is given. And what are these numbers, a and b? Well, these are the lengths of the projections of our point, the end point of the vector, to the corresponding axis which make up the coordinate axis. So, this particular segment, which is a projection onto the x-axis, is equal to 3 point something, and this particular projection on the point on the y-axis is 1 point something. So what we know is, maybe we don't know the lengths of this particular segment, but we do know its two projections on two orthogonal axes. Now, obviously we should use the theorem, Pythagorean theorem, to find the lengths, right? So this piece is equal to a, this piece is equal to b, so the length is equal to square root of a squared plus b squared, because this is the hypotenuse and these are two categories. So what I want to do, what I want to actually say that this is the formula for the lengths. Well, this is a two-dimensional case. Well, let's just spread it around. What if it's a one-dimensional vector? Well, one-dimensional vector is a vector which is represented on one particular single one-dimensional line, and again there are units of measurements here. And vector is again from 0 to some point, let's say to this point, or to this point, doesn't really matter. So in this particular case, the coordinate itself, like in this case it's 2.7. If the vector is directed towards the negative side, it will be minus something. So what would be the length? Well, the absolute value of this number, right? So in one-dimensional case, length is equal to absolute value of the number which represents, this is a one tuple, so to speak, one-dimensional vector in its analytic representation. By the way, these two formulas are not really different, because you can always put it like this. This is the same thing, right? So if one coordinate, it's square root of this one coordinate. If it's two coordinates, it's square root of sum of two coordinates. And now, obviously, we will go to three coordinates. And you will see that things is very much similar. Okay, the vector in a three-dimensional space. This is x, this is y, this is z. This is our point where the vector ends. Now this point can be projected onto the xy plane. So if this is ABC, then this would be A, this would be B, and this would be C. So imagine x0, y is a horizontal plane. Now the z-axis goes upwards. So from this point, I'm projecting to the xy plane. So this point is a projection of this point here. Now, what's the coordinates of this point, by the way? A, B, 0, right? And this height from the point itself to its projection on the xy plane is actually the third coordinate. So this is C. This is the same length. So again, this piece is equal to B. This piece is equal to A, which is this one. And this piece is equal to C. So what's the length of OA? OA. Now, the projection is B. And projection of B to these two are, let's say, C and D. Now, OA is a hypotenuse of a triangle ABO. So A is above the plane, B is its projection, so OB would be perpendicular to, so this is the right angle. So OA square is equal to AB square plus OB square. Now, OB square, now this is the hypotenuse, and this angle is the right angle, right? Because this is the projection onto this axis. So, AB square plus, instead of OB square, again, Pythagorean theorem, I will use OC square plus BC square plus this. So this angle is right angle. If you look at this from the top, right, it's a projection, which means we are directing the perpendicular. And now, what is this? AB square is basically C square, the third coordinate. Now, OC is our A square, and BC, same as OD, is B square. So again, we look at this and we see exactly the same thing, that the length of the vector is equal to square root of A square plus B square plus C square. So this is a typical situation with all the vectors, regardless of the dimensionality. With one vector, with one tuple representing a one-dimensional vector, we had the square root of its one and only coordinate. In two-dimensional case, the two-tuple AB. So the length is square root of A square plus B square. So again, it's sum of squares of coordinates. And in three-dimensional case, exactly the same thing. So basically, using this consideration, we can expand the definition of the length of the vector to any dimensionality. Now, I mentioned to you that vector can, for instance, represent the oil refinery, for instance, where all the parameters which are controlling the oil refineries are basically numerical components of this 100-dimensional tuple representing the state of the refinery. So the vector can be in 100 dimensions, right? So how to calculate the magnitude of this? Well, to tell you the truth, in case of oil refinery, it's very difficult to think about meaning of the vector. Meaning of the lengths, rather, of the vector, and direction. I mean, this space is not uniform. I mean, one component can be, let's say, a pressure and another a temperature. How can you combine together pressure and temperature? It's really hard to do. However, in some cases, when components are not so drastically different, then we probably can think about the meaning of the length of the vector. But in any case, from the mathematical standpoint, which is a pure abstraction, we can always introduce something like this. So if vector has the components, we can always think about the length, which is equal to square root of sum of their squares. So in this case, it does make sense. So basically, this is a definition of the lengths for all these strange situations. But in 1, 2, and 3 dimensions, it's quite an obvious thing that the formula is exactly what it is. And that's why it was expanded to other dimensions as well. Well, okay, so right now, we basically know what the length is, regardless of the way how we represent the vector. And we know about the geometric representation as just, an arrow-headed segment with a certain unit of measurement. You can just measure the length of the segment geometrically, or in case it's represented as a tuple, then something like this would be the formula to represent the length of the vector, which means we know what is the magnitude of this particular vector, what is the magnitude of the certain physical or a real object this vector represents, whether it's a speed or a force or anything like this. This is the strength of the force or the real speed of the velocity, something like this. Okay, so this is a preliminary lecture about the lengths. Probably there are certain problems which I will think about, and if I will come up with interesting problems, I will just put something in as a lecture. Meanwhile, you are obviously invited to take a look at everything else, whatever exists on Unizor, unizor.com, and take a little bit more time to register, to get engaged in enrollment in certain classes, and then you will be able to take exams, which is very useful, and you can take any number of exams and any number of times each exam until you will reach the perfection. So thanks very much and good luck. Hi, I'm Zor. Welcome to Unizor Education. We continue talking about vectors. We just recently covered the topic lengths of the vector, and we also visited the different representations of the vector, like a tuple or like a geometric, I don't know, some kind of a segment with an arrow. I mean, that's also a representation. So after that, let's just solve a few problems related to different representation of the vector and its lengths and how it's positioned in the space where it acts. So these few problems are very, very simple. Obviously, I do encourage you to go to unizor.com, go to vectors topic, and in the lengths lecture, under the length lecture, there are these problems listed, so try to do it yourself first, and then listen to this lecture. Okay, so problems are really simple, so don't think it will be any challenge or anything like that, but still it needs to be done just to make sure that you perfectly understand all these simple concepts. Okay, problem number one. It's just a conversion from one representation to another. So let's consider you have a two-dimensional plane with coordinates, and you have a vector originated at the beginning of the coordinate, at origin point. It has a length L and the angle phi with the positive direction of the x-axis. So this is a geometric representation. You have a length and you have a direction relative to some chosen direction. Now, what is required is to convert this particular representation into a tuple representation. Now, the tuple representation is basically the coordinates of the endpoint of this particular vector in this coordinate system. So all I need to do is I have to find coordinates of the endpoint of this vector, and that would be my tuple representation of the vector. Now, obviously, coordinates are, this is A, this is B, this is B, the same thing. And all we need to do right now is to use the plane trigonometry of the right triangle. The right triangle is obviously this one. The vector itself plays the role of hypotenuse, and the coordinates A and B are basically two catenae. So A is equal to L cosine of phi, and B is equal to L sine of phi. So this is a conversion from the geometric representation when the vector is represented by its lengths and direction relative to some chosen direction, angle from the chosen direction. And A and B are the symbolic representation in the tuple form, which is related obviously to coordinates. And in this particular case, what's important is that the horizontal x-axis, which is used as the one from which we actually tried to deviate in the directional movement, and it coincides actually with abscissa, with x-axis of the coordinate system. So that's explicitly used. Because if, for instance, this angle phi is angle from, I don't know, some other direction, then we have to do some, angle manipulation and conversion. But this is the simple case. That's all it's needed. Now, second problem is very much related to this. So let's consider that, again, we have a two-dimensional plane, and there is some point AB where an object is located at a certain time. But it's not just sits in this position, it actually moves with a constant speed, and the speed is again equals to L, which is represented by the length of this vector, and there is also a direction between horizontal line and the direction of the movement, which is phi. So my task is to represent this vector as a tuple. Now, I would like to recall the fact that the vectors are characterized by two things, length and direction, which means this vector, which also has a length phi, and which has an angle phi and the length L, it's exactly the same vector. These two vectors are equal, congruent, or whatever you want to say, which means that initial position, the beginning of the vector, has absolutely nothing to do with its tuple representation. Tuple representation of this vector and this vector are exactly the same because these are two vectors which have exactly the same lengths and exactly the same direction. So all vectors, this, and anywhere else, wherever I put, as long as they have the same lengths and the same direction relative to horizontal line, these all vectors are exactly the same. They are equal to each other, they're congruent to each other, and their tuple representation is exactly the same, which is position of the endpoint of this vector if it's originated at 0, 0. And we know this position is equal to L cosine phi and L sine of phi, as we did in the previous problem. So these two, L cosine phi and L sine phi, are the coordinates of the endpoint and the tuple representation of this particular vector, regardless of the beginning. So this is extraneous condition which we don't really need. It doesn't matter whether the point is at AB or anywhere else on the plane. All vectors with the same direction and the same lengths are the same. 3. Okay. Given vector in its tuple representation, minus 6, 6. So this is an endpoint of the vector originated at 0, 0, going towards this direction. So question is, what are its lengths and angle with the positive direction of the x-axis, which means this angle. Okay, now that's easy. The lengths, you can use this right triangle. Now minus 6 and 6 it means that basically the absolute value of these two category, the lengths of these two categories is the same. This is 45 degrees. So this is 135 degrees, which is what? 3 pi over 4, right? And 45 is pi over 4. So we know the direction, which is this. This is an angle, phi. And the length is basically right triangle, Pythagorean theorem. If this is 6 and this is 6, so you have 6 square plus 6 square, which is 6 square root of 2, right? So this is L, and this is phi. End of story. So mind you that I'm using the angle from the positive direction of the x-axis towards the direction of the angle. I mean, that's basically something which is sufficient to define the direction of this vector, right? I can probably start from any other point. I can start from the vertical point, in which case it's 45. Doesn't really matter. Traditionally, we do it from the x-axis. As you see, all problems are very, very simple and very basic. They are just based on the definition of the vector and its lengths, etc. Now, similar problem, different coordinates. So it's 6 minus 6. This is the vector. So what is the angle? It's either this one or this one. This is positive direction, this is negative direction. Well, obviously it's easier to use negative direction. It's obviously minus 45 degrees, so phi is equal to minus 45 degrees or minus pi over 4 in radians, right? This angle, phi. So negative angle minus pi over 4 is exactly the same as this one. And as far as the that's direction. Now, as far as the length is concerned, it's exactly the same length as in the previous case, because the lengths of these two categories are 6 and 6. So you have L is equal to 6 square root of 2. Easy. Next. Okay. Let's say we have 2 points. One point is AB, another point is CD. Now, we have an object which moves from here to there with a constant speed s. So, I have s, and I have AB and CD. Let's assume for simplicity that A is less than C, B is less than D, which means both coordinates are increasing. That's easier this way, so I don't have to worry about negative things. So, question is, what exactly are the characteristics of this particular vector of speed, or velocity rather, vector of velocity, which is the same in every point on its way, because I said that the s is constant. I hope I said it. If I didn't, I'm saying it right now. So s is constant. So it moves with a constant speed from this point to this point. Now, let's refer back to the first problem. I gave the length of the vector. Well, s is basically the length of the vector, right? That's the absolute value of the speed. And I was also using the angle, the direction, And from these two, L was the length, phi was an angle, I derived L cosine phi and L sine phi as tuple representation. So this is the geometric representation, this is a tuple representation, and that's how they're related. Now, I don't have exactly the same as in that particular problem. I do have length of the vector, which is in this case letter S, but I don't have a direction. Well, I don't have direction in explicit form, but I have 2 points which basically define the direction. So, how can I determine this angle? Well, it's easy, because this is A, this is B, this is C, and this is D. So, what do I know about this particular triangle? Well, I know this and this. These 2 categories I do know, because this vertical one is the difference between D and B, and that's where I'm using the D is greater than B, so this is positive. It's easier for me this way. Now, this catetus of this right triangle is obviously C minus A. Now, tangent of this angle is the ratio between the opposite catetus towards the adjacent one, right? The opposite is D minus B, adjacent is this. Now, considering these are all positive, and as I was saying, I'm looking for this particular case, I can resolve this as this. So if tangent of some angle, in this case it's an acute angle, the tangent of the acute angle is this, then angle itself is the inverse to tangent function called arctangent, which I'm sure you remember from the trigonometry course. If you don't, just go back to unizor.com. There is a trigonometry course where I explain what arctangent is. So, knowing this, I know the phi, I know the angle. And from the angle I can define cosine and sine, and if you want, you can obviously make some kind of a transformation from cosine of the angle tangent of which is equal to this. You can find what is the cosine and sine using very elementary trigonometry formulas. Considering the angle is acute, you will not have any problems with square roots, etc., etc. So basically that's it. All I wanted in this particular problem, in addition to whatever I did before, to define the angle phi if I have endpoints of the direction, because these endpoints do characterize the angle fully through its tangent in this case. Well, that's it for today. I do recommend you to do exactly the same problems just by yourself if you didn't do it before. Problems are very easy. Go to unizor.com, and I do encourage you to get registered as a student, have somebody else registered as your supervisor or your parent, and enroll you in classes, and that would enable you to take exams. You can take any number you can take exam any number of times until you will get it perfect, actually. So that's the purpose, and try to solve all these problems again yourself. That's very important. The whole course is oriented towards solving problems rather than just explaining certain simple things. So these problems are very important just to understand different representations of the vector. They're not difficult at all. Thanks very much, and good luck. Hi, I'm Zor. Welcome to Unizor Education. This lecture is about a couple of problems, very simple problems, related to vector and vector lengths. I strongly suggest you to try to solve these problems yourself first. They are presented on unizor.com website. It's a chapter dedicated to vectors, and the particular topic is lengths. I think it's problem number 2. Right, problem number 2. So, 2 easy problems related to vectors. In this case, these are vectors in 3-dimensional space. The first problem is the following. You have a vector represented as a tuple. Remember what tuple is? It's just 3 numbers in 3-dimensional system, which are coordinates of the end point of the vector. This is x, this is y, this is z, and this is the vector which has coordinates a, b, c, which means that its projection on 3 axes are correspondingly projection on the x, it's a, which is the same as this. Projection on the y is b, which is this, which is the same as this. And projection on the z is something like this, right? So this is C, and this is C, obviously. So try to imagine in 3-dimensional space. So these 2, x and y, are horizontal plane. Z goes up. Now this is the vector which has coordinates a, b, and c, and these are projections basically. This is projection on the xy plane, and from this point we have projections to x and y. This is projection on the z-axis. All right. So a, b, and c are given. What's necessary to find? Okay, number 1, lengths. Lengths of the vector a, b, c. Okay, L. Lengths. All right. So how can we find the lengths? Well, let's consider triangle OPQ. Now, PQ is a projection on the xy axis, which means it's perpendicular to all different lines, including OQ. So this is the right angle, 90 degrees. And it's a vertical right triangle. So OP is a hypotenuse, PQ is one catetus, and OQ is another catetus. We do know PQ. PQ is projection on the z-axis, right? Because that's the projection on the that's the segment which constitutes the distance from the point to projection on the xy plane, which means that the length of the segment is projection to the z-axis. So we know PQ. Now, do we know OQ? Because if we do, we can just use the Pythagorean theorem, right? Well, we don't know OQ easily, but we do know that OQ is a hypotenuse with A and B. This is also the right angle, right? Because from the Q, this line is perpendicular to OX. If you imagine this is XO, Y is a horizontal plane, we just look at this from the angle. But if you look at this from the top, that would be a perpendicular, right? So this is the right triangle, OQR. And in this right triangle, we do know OQ, because this is the hypotenuse with 2 catetus A and B. So OQ square equals to A square plus B square. Now OP square, which is the square of the lengths which we are looking, lengths of the vector, is OQ square plus plus PQ square. Which is equal to OQ square is A square plus B square, PQ is C, so we have A square plus B square plus C square. So the length OP L is equal to square root of A square plus B square plus C square. Which is absolutely similar to the lengths of the vector in two-dimensional space. Because if you have only two dimensions, let's say this and this, so forget about the bottom of the picture, then obviously the length is equal to, length square is equal to sum of these two squares, right? Because these are two projections and these are two coordinates. So for a two-dimensional case, it would be A square plus B square. Three-dimensional, A square plus B square plus C square. And actually, if we will go deeper into the higher levels of mathematics, the vectors in n-dimensional space, which have coordinates like a1, a2, a2, a3, an, they do have the lengths, which is defined now, it's a definition, as a1 square plus a2 square plus a3 square, etc., etc. Okay, so that's the lengths. Now, next, angle with axis x, y, and z. Well, these are, again, spatial angles. So try to bear with me. It's angle from vector OP, for instance, to vector OZ, or OX, or OY. So it's these, 1, 2, and 3. These angles. And again, try to imagine it in three-dimensional space. This vector OP sticks right in the middle of these three axes. The three axes are perpendicular to each other. Well, what do we know about these triangles? Well, look at this way. If you will connect, what do we have? We have more, let's say, M and N. If you connect P to point R, or P to point M, or P to point N, which we have already connected. Now, it's very easy to understand that these are perpendiculars to corresponding axes. So these are basically projections from the point P onto the corresponding axis. Q is a projection on the plane x or y. M is projection of the point P onto the y, because that's exactly what coordinates actually are, right? It's a projection of the point on the corresponding axis. And N is a projection to the z-axis. So, what do we know about each of these triangles? Let's say OPR, for instance. Well, we know that this is, L is a hypotenuse, and the catetus is A, because PR is perpendicular to OR. It's projections from the P to the axis. Same thing here. What do we know about triangle, let's say, OPM? Again, OP is a hypotenuse, the same hypotenuse, and this is one catetus, PM, and another catetus is B in this case. So, all these triangles, we have three triangles, their properties are, their hypotenuse is L, and one of the catetus is corresponding with A, B, or C. Now, we are looking for an angle which is adjacent to this particular catetus, or an angle adjacent to this particular catetus, or angle adjacent to this particular catetus. So let's go to the two-dimensional picture. So if you have a hypotenuse, which is always L, and one of the catetus, which is A or B or C, and you need to know angle phi, which is adjacent, how would you calculate the angle phi? Well, assuming that this particular point is has positive coordinates A, B, and C, just for simplicity, we can say that these angles are all acute, and cosine of phi is equal to A over L, capital L. So from this, we derive very simply that angles, let's call them phi 1, phi 2, and phi 3. So phi 1 is equal to arc cosine of A over L. Phi 2 is equal to arc cosine of B over L and C over L. So these are angles between the vector and the corresponding axis. And again, we derived it by projecting the endpoint of the vector onto each of the axes, and the projection point has the lengths A, B, and C, and lengths of the vector we have already calculated, which is this. So just substitute L into this formula and you will get one angle, and then instead of A, put B, and you will have another angle with the y-axis, and C for z-axis. And the last one about this particular problem is, let's consider, I think we have too many different things on this picture, so let's redraw it. Now we need an angle between the vector and its projections not onto the axis, but projections to the planes, coordinate planes. So let's just consider one of them. Okay, this is the one. We project the point P to point Q. So this is L, this is A, and this is A, this is B and B, this is the right angle. Now this is projection, so this is also the right angle. And we need an angle between OP and OQ. Well, basically it's very similar. What do we know about triangle OPQ? We know the hypotenuse OP. Now this is the right angle, right? We know one coordinate, which is PQ, which is a C coordinate, right? The z-axis projection. And then we don't know this particular catetus, but we don't really need it because we have this opposite catetus. So the angle can be calculated as sine of phi is equal to C over L, right? If this is phi, the opposite catetus towards hypotenuse. And we know L because we have already calculated it, right? So in this case, well, the only thing is, let's use, instead of phi, let's use psi. Which means psi 1 is equal to arc sine in this case. Sorry about this. Arc sine. Now, in this case, it's C over L, and in other cases, it's B over L and A over L. So the angle between vector OP and its projection on xy is arc sine C over L, where L is this. Now the angle between the vector and its projection on, let's say, XOZ plane would be the B over L in this case. And projection on YOZ plane would be arc sine of A over L. Well, that completes this problem. So I think all you need here, the problem is very simple, as long as you understand this spatial relationship, which angles are right angles, which angles are acute angles, etc. And again, it's easier for me to solve this problem with all positive A, B, and C, so my angle lies in the main, how's it called, octangle, octangle, whatever. The opposite to quadrant in two-dimensional case, we have octant, I guess, octant. So this is the main octant with all positive coordinates in the three-dimensional space. So we have to understand how this projection actually is working. I mean, I don't have these three-dimensional models to show you, so that's why I try to display it on the whiteboard, but basically that's what it is. Just imagine everything is happening in three-dimensional space. Next problem. Also easy and also requiring certain dimensionality of your vision. All right, so what do we know? We know about the vector. Well, it's basically kind of opposite problem. In this problem, in the previous problem, we knew the tuple representation A, B, and C. Now we know something else. We know the length of the vector. We know L. And we know these angles between the vector and its projection on each of the plane. So this is projection onto xy, so let's call this angle gamma. Now projection on the on this particular plane, it should be something like this, I guess. This point. So we know this point, and the vector projection is this, so we know this angle. Now this is xz, so we will call it beta, and then gamma, similarly. So what do we know to find out? Well, first of all, we have to know A, B, and C. Well, let's think about it. Again, it's very simple. What is z coordinate in this particular case? It's the length of this particular catetus, because this is at the right angle. It's perpendicular down to the plane, and this is one of the lines from this point. So the projection of OP would be OQ. We know L, we know gamma, so we know this opposite catetus, right? This PQ, which is z coordinate, right, which is C in our representation, is equal to, so catetus, if we know hypotenuse and opposite angle, right? So it's L times sine of gamma. And absolutely similarly, you will get that B is equal to L sine of beta, and A is equal to L sine of alpha. That's it, it's very simple. So all you have to understand is how this spatial arrangement is working. All right, next. And what are the lengths of three projections on the planes? Okay, so now it's asking what are these lengths of projections, OQ for instance? Well, but again, we know everything about this. We know this catetus and we know this catetus. So the projection OQ is equal to L cosine of gamma, right? This is catetus, this is hypotenuse, this is an angle adjacent. So the cosine of this angle is this over this. So this particular line, this particular segment, catetus, is equal to hypotenuse times the cosine. And similarly, all other, the projection, the length of the projection on the, let's say, xz would be L cosine beta, and correspondingly L cosine alpha. So, are these problems difficult? No, but let me repeat again. You really have to understand how it's all arranged in three-dimensional space. Well, other than that, I do suggest you to go back to the notes for this lecture. And again, they are on unizor.com in the vector chapter, topic called lengths. And just do it yourself. Try to draw your own picture of illustration of these problems and get the same results. I think it's a very useful exercise, and it helps you to visualize how everything is done in three-dimensional space. That's it for today. Thank you very much and good luck.